In this video, we're going to talk about what happens to spring constants when we combine springs together in different patterns. Suppose, for example, we just have two parallel springs, and each one has its own particular spring constant. Here we have K1 and K2. And imagine at the bottom here there's a horizontal bar, and we're pushing up on it, and we're doing it evenly so that if it moves up a distance of x on this end, then it also moves up the same distance x on that end. So each spring is going to be compressed then by the same amount, that distance x. So spring 1, this is going to push back down with the restoring force of F1. Likewise, spring 2 pushes down with the restoring force of F2. And this force, this restoring force F1, that's equal to the spring constant of that spring times the amount of displacement x. And here F2, that will be the same amount of displacement x multiplied by the spring constant for this spring. And the amount of force that we're pushing up, that of course will equal F1 plus F2. And then if we want to, we can rewrite F1 like this, likewise for F2. So our equation looks like this, where we can factor out the x and have it in this form. Now, let's remember what F is. That is the total force of the system. And the total displacement of the system, that's x, and of course that's the same everywhere. But if we divide the total force of the system by the displacement of the system, well, force divided by displacement, that of course is a spring constant. The total force on the system divided by the total displacement of the system, that's just x everywhere, but this divided by x, that would then be the spring constant for the entire system, F divided by x. And that spring constant for the entire system we call K equivalent, and then clearly that will just equal K1 plus K2. So when springs are in parallel, then their individual spring constants just add up. And hopefully that makes sense in terms of our everyday experience. If we have a parallel arrangement of springs, and they can have, say, all identical spring constants, I think that we have an intuitive feeling that would take more force to compress these springs than if we just had any one of these springs that we were pushing up against. So that's the system for parallel arrangement of springs. What if we have them now arranged in series? So let's consider this system. Here we have spring 1, and here we have spring 2. They have their own individual spring constants, K1 and K2. And before the mass was attached here to the system, they have their own natural length, and then the whole system gets stretched out. And if you watch that happen, you'll notice that each individual spring gets stretched out a different distance. So spring 1 would be, say, stretched out by a distance x1, and spring 2 would be stretched out by a distance of x2. So here is where one way in which the series system differs from the parallel system. In the parallel system, the displacement for the whole system was the same everywhere. Here, these are different. But there's another way now in which this system, the series system, differs from the parallel system. Now, attach the mass to this, it stretched the strings out, then of course the mass is just going to stay here. It's going to be vertically stable. So then, if the mass has a downward force of F, then obviously there is a restoring force F in the opposite direction. And where this differs from the parallel arrangement is that the upward restoring force F, it's the same for both spring 1 and spring 2. It's the same everywhere, as a matter of fact. And to understand that more, okay, we can understand here there has to be an upward restoring force F to balance the downward force F once this comes to rest after it stretches the springs out. Right here at the top of spring 2, then, there is an upward force F. Right here at this contact point. But then, by action and reaction, there has to be a downward force of same magnitude F on this contact point. So let's look at this system in a little bit more detail. Here we have the weight has a downward force of F, a restoring upward force of F from spring 2. That's right here, and here's the contact point. So if there is an upward force on this contact point of magnitude F, then there's a downward force by action-reaction. So on spring 1, then, we're saying at the bottom of the spring, there's a downward force of F. Well, once this has been stretched out, then of course the spring just stays stationary in its length. So if there's an F going downward in the bottom part of the spring, then there must be an upward force F of equal magnitude to keep the spring of constant length once it's been stretched out. So for us, what that means is that here there's an upward force F, an upward restoring force F, and at the top part of here there's an upward restoring point F. Some of these action-reaction pairs might cancel out along the way, but our upward restoring force F is the same throughout. Now, let's look down here. Here then, we have the weight attached, a downward force F, there's an upward restoring force F. Let's talk about the entire system now, for both the springs together. Then, of course, the basic equation is F equals a spring constant times the displacement. Well, here F will equal, now we have this spring has its own spring constant, this spring has its own spring constant. For the system as a whole, that will have an equivalent spring constant, and this restoring force F, the system as a whole gets displaced by x1 plus x2, the amount of displacements for each one of these individual springs. So F equals spring constant times the total displacement for the entire system. Then this would have to be multiplied by the spring constant for the entire system. So we have this equation. Now, this upward force F, as we just discussed, is the same for spring 1 and spring 2. So spring 1 has an upward restoring force equal in magnitude to F. Same thing for spring 2. But for spring 1, this is equal to the spring constant of spring 1 times its displacement. So that's K1, X1. And for here, for spring 2, that's going to equal its spring constant times its displacement. So we also have these two equations. Well, here in this equation, if we want, we can replace x1, that will equal F divided by K1. And we can replace x2, that will be F divided by K2. So let's rewrite this equation. We have F equals the spring constant for the entire system times x1, that was F divided by K1 plus F divided by K2. So now we've just simply rewritten this equation, substituting x1 is F over K1, x2 is F over K2. And now we can divide both sides of the equation by F to give us this expression. And then we can divide both sides of the equation by the spring constant for the entire system. And we have this equation. So this tells us how individual spring constants combine together to generate the spring constant for the entire system. And it might not be obvious the way it's written right now, but the spring constant for the entire system is putting both of these springs together. This is less than this K2, and it's also less than K1. And we can see that just by doing simple algebraic manipulation here. We have K EQ will equal K1 times K2 divided by K1 plus K2. So let's just write K2 over here to make it more clear. So obviously K2 is being multiplied by a fraction. It's being multiplied by K1, but K1 is divided by K1 plus K2. So of course this is just a fraction, therefore this is certainly less than K2. And of course we can also show, take K1 out, I'm multiplying K1 by a fraction now, so it's less than K1. And again, if we think about it, the fact that this is less than this one and it's less than that spring constant, if we think about it, that too should make sense in terms of our everyday experience. Suppose we have a spring like this. A long spring. And let's say it has a spring constant, call it KL for K long. And suppose we cut it off at the top. So now we have a short spring. So here we have K short. I think it's our feeling that it would be easier to compress this long spring than it would be the short spring that we obtained from cutting this one off at the top. And that's because this is less than this. We can think of the long spring as sort of being comprised of two short springs, K S1, K S2, where the spring constant of the entire spring, KL, that's less than this and this. So if we chop the spring off, we have two shorter springs. Each one of these shorter springs would be harder to compress than the longer spring. And again, that's because of this relationship that we've just proven. And of course, if we have more springs in series, then we just have more reciprocals here on this side of the equation. But let's talk about this relationship right here in a little bit more detail, because we're going to need that when we talk about double oscillators. So suppose that we have a spring its unstretched length we'll call capital L, as a spring constant K, has a spring constant of K, and its unstretched length is capital L. And then let's suppose we attach a mass to it so it gets stretched out somewhat. Like this. So we got a force F going down. And of course, once it gets stretched out and it stops, there's a corresponding restoring force F, and that restoring force F equals the spring constant, that's K, times the amount of displacement, and let's call that displacement X. So F equals Kx. So restoring force here on this mass M, that is equal to the spring constant of our spring times the amount of displacement X. Now, let's consider this part of the spring though. Let's say that we're right here, and this spring has a length of small l. And if we were to cut the large spring off, so we have this spring of small l, what spring constant would it have? Call it K1 for right now. Well, first let's consider this question. If for the shorter part of the spring it's of length L, when we add the mass to it and the bottom part of it got displaced at distance x, how far will this point get displaced? This was distance L. Now that gets stretched down a distance, but how far is that distance? And the answer is it's equal to small l, that part of the spring here, divided by capital L, times the displacement for the bottom part of the spring. So this was of length L, then we added the weight to it, and this gets displaced down to here, this distance, small l divided by capital L times x. Of course, if we were all the way down here, that small l equaled capital L, then it would just be the displacement x. See if you can convince yourself that's true. If you're not entirely convinced, look in video 10, and you will see that we derived this relationship in more detail. But indeed, if the bottom of the spring gets stretched out this distance, any part of the spring along the way gets stretched out this distance. Now, as we just discussed, the upward restoring force F, that's the same everywhere. So if we want to talk about this section here as if it's an independent spring with its own particular spring constant, then we would say, well, F, that is the same everywhere, what's that equal to? Its spring constant for this part of the spring, K1, times its displacement, that's this. So we have this equation. And again, this comes about because the restoring force F, that's the same everywhere. Now we're looking at this section of the spring as if it's an independent spring with its own spring constant. So again, the force F, that's the same up here as it was down here. That has to equal that spring constant times the displacement for it. And that is that. So let's write this. This we're going to write down here. We have F equals K1 times L over capital L times X. Now let's divide both sides of the equation by x. Well, F divided by x, that's K. That's the spring constant for the whole spring of length L. So this is K, and that equals this is K1. That would be for just this section of the spring. And we have then the simple equation. Or we could say K1 equals big L divided by small l times K. So let's say that we have a spring like this. It has a spring constant K, and it has a length of L. And let's say we take just a third of it. And we want to know if we cut the spring off, what then would be that spring constant. So we have K1 equals L divided by small l, that's L over 3, times K, or we have K1 equals 3K. So if we take a third of the spring, then that spring would be 3 times as stiff as the spring of the entire length L. Okay, that's all we wanted to show in this video, but we did want to go over this in some detail because in video number 12, when we consider the double oscillator, we're going to make use of this information. And again, we've been referring to different videos here. Video number 10 is where we discuss a spring so massive that you can't ignore its weight, and that's a fairly complicated system. And then in video 12 we'll consider the double oscillator. Anyway, the playlist for all the videos is at the website digital-university.org.